It's done. Okay, so the motive of the session is to teach you that how do we make subsets and how do we construct permutations. Now there are multiple ways of doing it, so we'll be talking of two ways each. So how do we make subsets using the recursive way, and how do we make subsets using bit masking? And also for permutations, so there's a STL that we can use, right? So there's a STL way and there's also a recursive way of doing it. Now I'll be coding along. I've not written any code right now, so I'll be coding and then teaching you along. So firstly, let's get started with what these things are. Now I hope that most of you already know it, but even if you don't, then there's nothing to worry. I'm going to teach it from the very scratch. Cool. So what's a permutation? So a permutation, or what's a subset? Firstly, let's talk about subsets. So let's say 1, 2 and 3 are the numbers that are given to me. Now in how many ways can I take numbers out of it? So I can say that, okay, I can just take a 1, I can just take a 2, right? I can take nothing, so that would be empty set, right? I can make a 3, right? Or I can take a 1 and a 2. I can take a 2 and a 3, right? Or I can take 1, 2 and 3. Let's count the number of permutations I got. 1, 2, 3, 4, 5, 6, 7. So there had to be 8. So there's definitely one I'm missing. So 1, 3 is one of the permutations. Now why are there 8 permutations in total? Or how do I know that? So for any set, there would be 2 to the power n permutations. Oh, sorry, 2 to the power n subsets, not permutations. Apologies for that. So yeah, 2 to the power n subsets are possible. Now how do we come up with this number 2 to the power n? So that is because for every number, right? Let me share this iPad. So cool. Yeah. Okay. So for every number, I have two possibilities. So if this is the array that I have, right? And it has some numbers in it. So this is 0, this is 1, this is 5, this is 7, right? So for every number, I have two possibilities. I can either add it, right? Or I can neglect it, right? So there are two possibilities for 0 of either being added or not, two possibilities for 1, two possibilities of 5, for 5, two possibilities of 7, or basically for all the n elements, I'm having two possibilities, not 5 and 7, but yeah, 2 and 2. So for all of those n elements, I'm having two possibilities. So they become 2 multiplied n times, right? This is n times. So in total, we are having 2 to the power n subsets from any given set, right? Now the question is, how do we make it? So let's discuss the recursive approach. That's way too intuitive, right? And then we'll also discuss about how to do that with bit masking itself. So let's discuss the recursive approach. This is my recursive function, right? I'll have to give it an index. Okay, so let's just start with the basics. So let me make a vector, right? Let's call it v. Let's populate some elements like 1, 2, 3. That sounds good enough, right? Cool. So what do I do now? So I describe my recursive function that it will get a parameter that would be the index. What is the index of the current element I'm standing at, and what's the vector I have, right? Okay. Now at each element I have two choices. One is to, okay, so two choices. One of them is to add it to the index, right? The other is to remove it. But how do I know which character I have used or which character I haven't? So let's utilize a vector int for that, right? Or let's call it subsets. That sounds cool. Let's just append it. Yeah. Okay. So if I'm gonna add it, so the first choice is that let's not add it. So let's just keep it absent. Let's not add it. So not adding. Right. So if I'm not adding, I'll say that okay, I'm not gonna add it. Let's move on to the next index, right? And pass the vector along, and then pass the subsets along. This makes sense. The other option is let's just add this particular element. So I'm gonna add this particular element to my subsets. So I'm gonna say subtract.push back the current value, that would be idx, right? And then I'm gonna call the recursive function. Now I've already added the value to the subsets. At the end, I'm gonna take it back because my work is done. Let's take this element back so that this particular array can be reused. That makes sense. And the terminating condition would be if I have reached the end of the array, right? Now from here I cannot go anywhere, right? So let's just return and let me print the array. So there could be two cases. So I could have actually got a empty set. In that case, if my subsets dot size is equal to 0, right? If it's 0, then you see out empty set, or rather than that, what I can do is I can start it with this sign, and then I can print my subsets, and then I'll close it with this sign. That would look better. And yeah, it's not a int function, it's actually a void function. So I hope the code seems to be fine to you guys. And over here, let's just clear the subsets. Let's call it so recursive of 0 comma v comma, or yeah, v comma subsets. That makes sense. Let's just do 1. Let's remove the cin statements. Let's see what it gives us. Okay, you guys there?
Yes.
Okay, cool. So see, so what we are doing is that there are two choices. So not considering the current element, considering the current element, that is v of idx as one of the subset elements, right? This is considering, okay, so not considering, I made a call, so that is this call. Then I said let's consider this element, push this element to the stack or to the subset, move ahead, take back the element from the subsets. This is required to keep it clean, so this is required to keep, okay, to keep it clean, right? Cool. So we were able to generate this. Now let's have a look. So firstly, I'm saying one of the subset is an empty subset. That's cool. One of the subset is the one that just contains 3 in it. One just contains 2 in it. There's another which contains 2 and 3. There's another that just contains 1. Another which contains 1 and 3, 1 and 2, and 1, 2 and 3. So in this way, we are able to generate all the subsets from a recursive function, right? So that is the very first thing we wanted to know, that how do we construct subsets using a recursive approach. That makes sense?
Yes.
Someone has a doubt? Okay, cool. So over here you can see that we constructed all of these subsets, right? So we had an empty set, a set with 1, 2, 1, 2, 3, 1, 3, 2, 3, and 1, 2, 3. So yeah, in this approach we'll be able to construct all the subsets. Now, is there a different way to do this? Yes, there definitely is a different way to do this. So let's say we don't want to use this iterative approach. We rather want to use something that is known as bit masking. So I already told you that 2 to power n subsets can be present, right? 2 to power n subsets would be that. Interestingly enough, if I have a string of length n, right? Okay, let me just show you in the iPad first so that it makes more sense to you. Okay, so over here I told you that for each of these elements you are having two choices, that you can either keep it or you can mark it absent. So for each of these elements you were having two choices, that was 0 and 1, where 0 denotes the absence and 1 denotes the presence, right? So over here also 0, 1. But wait, if I am having only two possibilities, 0 and 1 of a length n, then this particular this means that this is a binary string, right? Binary string of length n, right? So if I take a binary string, what I'll have to check is that whether if that particular element is set to 1, so it has two options, 0 and 1. If that particular element is set to 1, then I'll consider it into my subset. If it's set to 0, I'll not consider it. But what do I mean by that is, let's say these were the element I was having, that is 1, 2 and 3. Then I took a binary string, let's say 0, 1, 1. So I'll check that, okay, is this particular index set to 0 or 1? It's set to 0. I'll not consider this. Is this set to 1 or 1 or 0? It's 1. So let's consider this. So I'll add 2 to my set. Is it 1 over here or 0 over here? It's a 1. So I'll add this to my subset. So this would be the answer I'll be getting, right? Another case, if I had all zeros, so it would have said that, okay, no index is set. So the array which I would have gotten is an empty set or the empty array. Another case, let's say everything was set to 1. Then I would have added each of the elements. So I would have got 1, 2 and 3. The concept is pretty easy, I believe, but if you still have doubts in it, you can let me know. I'll be else I'll be moving ahead to the coding part itself. Guys, do you have any
So,
doubt? Yeah.
in the bit masking,
Hmm.
it will count from 000 to 111, just like we count in binary numbers,
Right,
right?
right. So we'll be doing that over
Okay.
here. So I know that 2 to power n would be there. So firstly, I'll need to run a loop. Okay, let's just not remove the comments. Okay, so let's just call it a binary string, and I can represent a binary string of length n in a binary in a number itself, right? So my numbers would
Mm.
range from, okay, let's call it b, would range from b is equal to 0 till the time, okay, so b is less than 1 to power n. Now I am doing this. Okay, so as you said that my numbers would vary from all zeros to all ones, right? Now let's say I had n ones, uh, n number of ones. So the number that would be just greater than this would be a single one followed by n zeros, right?
Yeah.
Make sense? Cool. So that's what I'm doing over here. So this is number one followed by n zeros. So the last number I'm gonna check should be smaller than this. Cool. This is what I'm gonna do. Okay. Then I'm gonna go through all the elements of the array. So over here we have just three elements. I'll go through them. I'll see that if the ith bit is set. Now how do I check that? Weird thing. So what I can do is, if my, okay, so over here 3 was actually, n is actually 3, so I can put it manually. I'll check that if my I, right, okay, or if one of I, if I move it I places, that's weird. Okay, give me a second. Cool. So over here I'm going from, okay, so I'll be getting something like 001, 002, so on and so forth, right? So I'll have to check if b and 1 I. So if this particular bit is set, then I want to add it to my array, right? So let's say this was my result array or the result subset I'm considering, right? If this is set, then I want to add this element. So I'll add the element I. Then I'll print the arrays. Let's see this in practice. Let's see this in action. If it works, if it fails, what happens? Let's just see. Okay, so over here you can see that firstly we generated empty set, then we generated a set with 1, with a 2, with a 1 2, with 3 1 3 1, then 2 3, then 1 2 3. So cool, I hope this works, right? This is working perfectly fine. We can check for even bigger numbers. So let's say the things were a bit different. So these were the three numbers we were having, right? So this is still 3. Let's try for 5 numbers maybe. Any guesses what are the number of sets we'll be able to get for 5 numbers?
2 to the power 5.
32 sets exactly, yeah. So over
Yeah.
here if you want you can count, these would be 32 sets. So we are able to generate all the sets using this logic. Sounds cool. And does it sounds easy as well?
This is a really smart approach.
Yeah, actually I've not made the code so I'm not the author for this, but yeah, whoever came up with this was actually smart. But it's too intuitive as well, I'll say. So if you understand binary numbers, this approach is actually pretty easy. You just have to check that whether that particular bit is set or not, right? If it's set,
Yeah,
ignore it.
that's the only part that is tricky. Everything else is easy here.
I think even that is easy. It could be the case that if you're new to binary numbers and stuff, you might think this to be tricky. It's not tricky per se. It just take common sense that okay, since for every number you are just having two possibilities, right? So that can be actually represented using a binary string, and using that you can generate it. So yeah, it comes with practice. Uh, I can comment on that actually. Cool enough. So yeah. So any doubts? So far so good.
Yes.
Okay, cool. Guys, I hope I'm not rushing it up. You can actually point it out, or you can tell me if I'm rushing things up a bit. Let's go for the next thing, that is generating the permutations. Now, what are permutations? Permutations. Okay, let's call it permutations. So, what are permutations? So, let's say I have three numbers 1, 2, 3. Now, over here, this is a permutation because this contains all the numbers. So, any arrangement of these three numbers is called a permutation, right? So 1 2 3 is a permutation, 2 1 3 is a permutation, so is 1 3 2, right? 1 3 2, right? Or we can say for n for array of n numbers, right, we'll be having n factorial permutations in total, right? So over here n was 3, so we'll technically be having 6 permutations. So other would be 3 1 2, then we'll be having 3 2 1, then we'll have 2 3 1. Cool. So these are 3 permutations we can have. So there are 6 permutations we can have. The order of permutation is basically n factorial. So over here n is 3, so the answer is 3 into 2 into 1, that is equal to 6. So we'll be having 6 permutations, and these permutations have been listed over here. Cool. Now how do we do this? So we can take help of a different thing. So initially, when we were talking about subsets, okay, let me go to the iPad. So over here, I was saying that for every element, right? For every element, I have two choices, 0 and 1. But in case of permutation, I don't have any choices in case of elements, but I have choices in case of indices. So I can say that at this particular index, let's say this is the 0th index of the final permutation I'm going to construct. Over here, I can keep any of the unused elements, right? So let's say my array was 1 2 3, right? So at the 0th position, I can keep any of these 3 elements. Then I'll come to the next position. Over here, I can keep any of the unused elements. Let's say I use 3, so I'm left with 1 and 2. I can use any one of these. At the end, I can use any one of these, right? Any one of the left ones. I'll move ahead. I'll say, okay, the permutation is actually complete. I can print that out. So that's what I'm going to use. I'm going to stand at a particular index. I can try for all the options I currently have, and then I'll move forward to the next index. So over here, I'll be actually traversing on the indices of the final permutation I'm going to construct, and not on the indices of the initial array I'm given. That makes sense, because if that doesn't make sense, I'll have to explain that again. But if that makes sense, things would actually be pretty easy for you.
I understood.
Anyone else? So guys, if you have a doubt, let me know. Otherwise, these sessions are of no use, like if you still have doubts after these sessions. Okay, we have some comments. Okay, these are your comments, right?
I just screenshotted the code.
Oh, cool. Thanks, man. Uh,
Yeah, yours.
so I hope there are no doubts. So let's move ahead. So that's what I'm gonna do. Let's call it void perms. Okay, I'm having some problem typing right now. Cool. Okay, and then I'm gonna give it the vector that's actually required. Right. Let me give it another vector called used. Now what is this? This would be required because for every element, I want to tell my algorithm that whether that particular element has been used or not. Because I want that every element should be utilized exactly once, right? So I'll be using another vector called used. What after that? So, okay. Which is the current permutation you're constructing? So perm or current perm, or you can say p. Okay. Then I'll check that if my p dot size is equal to v dot size, that technically means I actually have n elements in my permutation and I have to return over here. But before returning, I actually want to see what my permutation looks like. So let's just print it. So I'll print it with the open ended loop like this. Okay. And then p, right? And then I'll close it. Let's just give it some spaces. Cool enough. But if that's not the case, then what I have to do? So there are still some elements that are not used and I would like to use them. So I'll go through all of those elements. I'll go from 0th element to the last element, right? Okay, I'll check. Okay, if the current element is not used, if not used, right, in that case I can use it. So I'll firstly set it to be used so that I don't use it again. Then I'll say that, okay, insert this particular element in my permutation. So I'll be using this element. Then I'll say, okay, make the recursive call. So I'll say vi, then used, then p. Cool. And then once I've used it, so I have to make the array. So right now the array is dirty, right? We made some changes into that. We want to reverse those changes. So I'll say, I'll just reverse the changes I did. So I'll remove it from the array I added, and I'll also make used as 0 back. After that, you don't have to do anything. So yeah, that's the code for it. Let's try this thing out now. Okay. So I'll say that vector int v, right? Let's just make a simple thing just to test 1 2 3. and I'm going to use the permutation, and over there I'm going to pass my v, but I also need to pass another vector that would be the boolean vector. So let me pass that also. So used, it should be of size 3, and all of the elements are initially set to 0 because they are not used. So I'll say used, right? What about p? So over here, yeah, just small thing. So whenever you are passing functions, right, and you don't want the program to take a lot of memory, always try to use pointers or references to the functions. Okay, let's call it p. Right, let's pass p. Let's see what it gives us, whether it works, it fails, what happens. Okay, okay, so we got a 1 2 3, right? We got a 1 3 2, we got a 2 1 3, we got a 2 3 1, we got a 3 1 2, that then we got a 3 2 1. That is exactly the permutation we expected, right? And the total count is 6. All of these numbers are different and the total count is 6. Let's try for a bigger number. Maybe let's try for 4 more digits. So let's call it 1 2 3. Then we have some other numbers like this, right? Or 2 more numbers over here. Let's try this out. Let's see what happens. Any guesses what would be the count of the permutations we have received over here? Any guesses so far?
Uh, it will be 5 factorial. I think that is 120.
Yep, right. So yeah, it would be 5 factorial. So 5 factorial basically 5 into 4 into 3 into 2. So this is 20, this is 60, this is 120, right? So yeah, 120 into a total you will be getting. So this is the way you generate permutations. Is that all fine? You understood the concept or any doubts?
I understood.
You understood? Anyone else? Okay, so I see a few thumbs up. Cool. Now, but is it recommended for you to utilize this way when you are coding, right? So would you like to write these like 15 lines of code every time you are using a permutation in context itself? Not actually. All the permutation kind of questions are rarely asked, wherein you actually have to enumerate all the possibilities. But there's a SQL feature. So what you can do is you can start a while loop, right? You just write over there next permutation, right? You have to give the array, and it will print all the possibilities for you. P, and then you have to. Cool. Okay, just have to this. This makes sense, I guess. Let's try it out.
You forgot the curly braces,
Where?
the ending brace uh, for the solve function
Which one?
after the while loop. After the while loop.
Oh, got it. Cool. Let's try this. It's gonna work. Is it not gonna work? Let's see. Okay, it gave us. Okay, we are actually printing V. We were supposed to print V. Okay, cool. Let's try it again. Cool. So it worked again, right? So it's right.
What is that next permutation function?
Yeah, that's what I'm gonna explain. But before I explain that, let me do a small trick. Let me change the way the indices are over here. Let's make it in this fashion, right? Or let me change it even further. Let's make it 16 5 3 2 and 1. Technically it shouldn't have made any difference, right? You still are having those elements, right? So it shouldn't have mattered, but let's see what happens. So over here you were still getting the right answer, but as soon as I do that, my answer changes, right? So I'm getting a single element. That's weird, but why is this happening? So that's the actual question. So that brings us to what this function is actually doing. So what this function actually does is that it takes in a vector or any container for that matter. Now on that particular container, you understand the meaning of a container, right? So anything that contains elements
Uh,
into it, it could be a vector, it could be anything of that sorts, right? So it's
oh
taking a
yeah.
vector
Okay.
over here, right? So on this particular vector, it will try to give me, or it will try to change this particular vector so that it is just bigger than that. Now what do I mean by just bigger than that? So let's say your vector was 1 2 and 3. Right now it's completely sorted in ascending order, right? Or we can say its rank is 0, right? Since it's sorted in ascending order, its rank is 0 right now, right? It will give me 1 3 and 2. Why is that the case? Because its rank is 1. Now 1 3 2 is greater than 1 1 2 3, but there's no other way which or other array which can lie between these two. What would be the next? So next would be 2 1 3, right? This would have a rank 2, right? Then it will give me 2 3 1, right? This would have a rank
The
3.
last one will be the greatest one, right?
Yep, the last one. So there would be some permutations like this, right? So there would be like around
Lexicographical order, Hitachi,
yeah,
right?
lexicographical order is what you can say. So at the last you will be getting 3 to 1, right? And its rank would be 5, right? Okay, there was just one I could have actually written it. So this would be 3 1 2, right? This its rank would be 4, and at the end it will giving us it would give us this. We can actually check it. So let me pass 1 2 3 and let's see this. Cool. If we pass 1 2 3, we get 1 2 3 as the first thing. That's good. Then we get 1 3 2. That's fine. Then we get 2 1 3, then 2 3 1, then 3 1 2, then 3 2 1. Perfectly fine, right? It exactly matches. But the problem is, if I pass something that is not at this particular level, then it will start at that particular level itself. Now let's say I pass 2 1 3 to it, right? So it's gonna start at this particular level. So it will not like show me these two values. So if I try that, I'm trying with 2 1 3. So technically I'll be seeing only these four values, right? So yeah, I'm seeing 2 1 3, then 2 3 1, then 3 1 2, then 3 2 1. That is because it's just trying to increase the level of that particular permutation. That's exactly what it's doing. Until and unless it reaches the end, it will keep doing it. So it's always recommended, if you're using this particular approach, before sending it, always sort the array. Make sense? If you sort it, no matter how you write it, it's always going to give you the right answer, because it's going to sort it first and then it's going to pass it. Now the reason of using a do while and not a while loop is because had you used a while loop, then in the first iteration itself, it would have changed the array, right? So it would have changed the array. It would have started from 1 3 2, even if you passed a right array that is 1 2 3 into it. But we wanted to work on all the permutations possible. Hence we are using a do while loop over here, so that it goes through all the possibilities. Cool enough?
Yep.
Okay, guys. So how was this? Did you like this? Can I change something? Cool, guys. So yeah,
One question I have.
yeah, sure, shoot.
Where does next permutation function come from? Is it in a library?
Bro, your voice is breaking a lot actually.
I'm asking, where does that next permutation function come from? Is it in a library?
Yeah. So whatever things I'm using, they are all available in bit standard C++.h, right? It would be available in a
Okay, so
lot of other
that
libraries as well, but this is the library I'm using. So if you want to check that, you can Google it up. It will tell you that in what all libraries it's available. But yeah, this is one of the, you can say, a superset library. A lot of functionalities is already available in it.
okay.
You had
Thanks, then.
yeah.
I understood everything actually.